Welcome to the structural analysis course. So in the last module we have started our last topic, that is how to analyze the indeterminate structures. So we have seen two methods. First method was three moment equation, and in the last class we have seen the moment distribution method to solve the indeterminate structures. So today we'll see another method to solve the indeterminate structure, that is slope deflection equations. Based on slope deflection equations, how we can solve the indeterminate structures. So let's begin our derivation part first. So before starting derivation, let's understand few basic things about analyzing of indeterminate structures. So there are broadly two methods of solving the indeterminate structure. One is force method, and next is displacement method. So all the methods can be classified into these two large categories: displacement method. So one is force method and next one is displacement based method. So whatever we discussed in the last class, so displacement method has based method has two subtype. So first one is moment distribution method, what we discussed in the last class, and moment distribution method, and second one is today what we will discuss, that is the slope displacement deflection method. So these are the major classifications to solve indeterminate structures. So let me just again explain this part. First method is force method and second one is displacement based method. So what is force method then? So in the force method, our primarily unknowns will be the reactions, right? As we have seen already, what is indeterminate structure? Indeterminate structure means number of unknown reactions are more than the available equilibrium of equations. So we have to use extra compatibility equations to solve those indeterminate structures, right? So in the force method, our primary unknown is the reactions, unknown reactions, forces. So forces are primary unknown. So based on the forces, we formulate our equation and then we solve it. So those type of methods, we call it force based method or force method. Now in displacement methods, basically our unknowns are primarily displacements of a structure. We consider that as an unknown and then we derive our equations to solve the indeterminate structures. So in the displacement based method, there are two subtypes. One is moment distribution method, another is slope deflection. So in the last class, we have seen moment distribution method, how we can use moment distribution method to solve simply the distributing the unbalanced moment into the nearest supports. We can easily solve we can easily analyze the indeterminate structure. So today we will see how we can use slope deflection equations to solve the indeterminate structures. So let's get started. So initially we'll try to derive the equations of slope deflection and then we'll try to solve it. So what is this method name? Method name is slope deflection equation method. So basically we have to derive a equation which relates slope and deflection in a building or in a structure, basically with moments, and that will give us slope deflection equations. So as I was mentioning, so this method is useful when the structure is indeterminate structure. So let's say this is an indeterminate structure, right? This is a propped cantilever which one end is fixed, another end is roller, and the concentrated load is acting P. So because of this load, a concentrated load, the beam will undergo deflection. So this is the deflected shape of a beam. So here in these methods, we have to understand few more things. What is degree of freedom? So first we have to understand is degree of freedom. What is the meaning of degree of freedom? Already you know, I think many of you know what is degree of freedom, but still I'll explain once again here. So degree of freedom means for a particular, so the structure is consist of many joints, right? So each joint can rotate or can move in any directions, right? Any point, if you look into any 3D structure, if you consider, or even in 2D structure, each point can move into any direction freely. That we call a degree of freedom. So how many ways the point can move independently, so that we call it degrees of freedom. So for example, in a 3D structure, So this point or any point can move into horizontal direction, can move into vertical direction, or can move into z direction also. So you have three translation as well as three rotation also. So this point can rotate about x-axis, this point can rotate about y-axis, and this point can rotate about z-axis. So each point in a 3D structure has total 6 degrees of freedom. So 3 translation and 3 rotation. So here we will talk about kinematic degrees of freedom. So for example, this beam, this point, if you consider B is a roller support, right? So roller support cannot move into all the 6 directions, whatever I mentioned. So total each point in general in a 3D structure, each point has 6 degrees of freedom, right? 3 translation and 3 rotation. But if you see this point B, so B is a roller support. So roller support cannot move all the 6 directions. It can move only, if you consider 2D structure, then it can move only this horizontal direction. It is easily freely can rotate, and another thing is the rotation, that is it can rotate about z-axis. So these 2 degrees of freedoms are open for this B, although in 2D structure it should have 3 degrees of freedom, but vertical degrees of freedoms are restrained. So this B point cannot move vertically up and down, whereas this point B can move easily in the horizontal direction, and it can rotate also about z-axis, the point B. So, although each point in 2D structure has 3 degrees of freedom, and in 3D structure it has 6 degrees of freedom, right? So here this is a 2D structure, so each point should have 3 degrees of freedom. So, but the joint B is a roller support, so that's why it has 2 degrees of freedom. So that 2 we call it kinematic degrees of freedom. So the joint B has kinematic degrees of freedom by 2. Like in 2 directions, the B joint B can move. One is this rotation, another is horizontally. So now if you see this B point, actually, and that this B is connected to A, right? So this is a AB is a propped cantilever. So A is a fixed support. Fixed support means the point A cannot move into any direction. Although each point has 3 degrees of freedom, means 3 direction it can move easily, freely, but the A is a fixed support. So that's why the point A cannot move in any direction, right? It cannot move into up, it cannot move into horizontal, it cannot rotate also. So all these things are restrained in A, right? So now if you consider this beam is inextensible, so if you pull down from B, the beam is not extending. So in that case, the B can move in this direction also, but because this member is inextensible, it cannot extend it. The made up of material of this beam is such that this is inextensible, it cannot extend it, right? So now B is also can rotate in this direction, but because of inextensibility of this member, this moment also restrained. So now I effectively the joint B has only 1 degree of freedom, kinematic degrees of freedom, that is the rotation, right? So like that, in this method we have to find, first we have to identify how many kinematic degrees of freedoms are there and at each joint. So once we know the kinematic degrees of freedom, then based on that kinematic degrees of freedom, we have to derive our moment slope deflection equations. So now let's derive our main slope deflection equation. So before deriving, let's consider a beam of simply supported beam. Let me draw it quickly here. So this is a simply supported beam of one, both the hands are, for example, hinge, and maybe some arbitrary loads are acting. So any loads are acting. So this end is A end and this end is B end. So now if you see, this beam is simply supported beam. Both ends are hinge. So it is an indeterminate beam also. So and some random loads are acting on it. So once application of load, the beam undergoes deflection. So the deflected shape of the beam will be maybe in this format. So this may be the deflected shape of a beam. Now, and this may be theta A. So angle making with tangent theta A. Similarly, this may be theta B. Right. So now in this method, first what we have to do is similar to last method, similar to moment distribution method. What we did, we fixed, we locked all the supports. So here also we have to lock all the supports in this method. So once you lock all the supports, the fixed end moment will be generated at A and B. Although this support is a hinge, this support also hinge, but in this method first we will lock all the supports. So once you lock it, fixed end moment will be generated in the support. So now let's do it one by one. So for now this is a fixed roller simply supported beam where only one side MAB one moment is acting on it. So let's consider at the step 1 some moment is acting at B, which is nothing but MBA dash. So only this is the first instant, only this MBA load moment is acting at and A and B. Now because of this external moment, also the beam undergoes deflection. So this is the maybe another deflection may be happening because of MBA. Only there is no load is acting, only MBA external moment, some moments is acting on it at B. So because of this there will be deflections in a beam. And now using the moment, using the moment area method or conjugate beam method, any method you can employ and find it out what is theta B and theta A. So these are the values theta b and theta a. If you just use simply moment distribution method, moment area method or conjugate beam method, whatever we discussed earlier, we can easily calculate slope and deflections, right? So after application of BA at B, that much theta b will be generated here, and theta a at this end a theta value this much. So easily you can compute both the values. Now in the second instance, this is the first instance where you applied only m dash ba, and that much is the theta a and theta b. Now remove this mba and apply another moment in this side, that is m dash ab. Similarly m dash ab we apply at a and there is no moment at b. Now we remove this one and we apply another moment at end a. Now again the beam will undergo deflection, and the deflection theta a dash theta b dash will be these two values. So these values can be easily computed using the moment area method or conjugate beam method. Easily we can compute. So now together, if both the forces are acting MBA and MAB, if both the moments are acting together, then how much will be the theta A? So theta A will be nothing but this plus this. So both if you add, so theta A means this plus this. So theta A will be, this will MABL and minus MBAL into 6EI. So this is the net theta when the both moments are acting. That is M dash BA and M dash AB. Both moments are acting. Similarly, theta B also can be computed. This value plus this value will be theta B. Right. So now theta A and theta B is computed. Now theta B and theta A both can be written in terms of MAB also. MAB, M dash AB and M dash BA also. So now if you reorganize both the equations, then both the equations can be written in this format also. In terms of theta A and theta B, if you just reorganize both the equations, you will get MAB dash equal to this value. Similarly, MBA dash equal to this value. 2EI by L into 2 theta A plus theta B. Similarly, at M dash BA will be 2EI by L into 2 theta B plus 2 theta A. Now, what is the net moment at A and B? As already I mentioned, that we have restrained both the ends. A and B, both are restrained, right? Means fixed. So there will be fixed end moment also. So fixed end moment, so net moment at A will be MAB is equal to nothing but fixed end moment plus M dash AB. Okay, so fixed end moment plus M dash AB is the net moment at A. Similarly, net moment at B will be fixed end moment at BA plus M dash BA. Right, so this is a net moment MAB and MBA. Now if you substitute m dash ab value, we just computed this value, and m dash ba value, we just computed this value. Just substitute these two equations, we will get, this is our final equation for mab and mba. So mab equal to, very easy to remember both the equations. See, mab equal to MAB fixed end moment plus 2EI by L into 2 theta A, because as we are computing A to B, so in that case it will be 2 theta A, means 2 times the near end plus 1 times far end. So if you are considering AB means the near end will be A and far end will be B, right? So MAB will be fixed end moment of AB plus 2EI by L into 2 theta A plus 2 theta B, whereas MBA will be fixed end moment of BA plus 2EI by L into 2 theta B plus theta A, right? 2 times of near end. So when you are computing MBA, so BA's near end is B, whereas far end is A, right? So 2 into theta B plus theta A will give you MBA. So these two equations are nothing but slope deflection equation. So in these equations you have to remember very easy to remember also. MBA equal to fixed moment of MAB, sorry, MAB equal to fixed moment of MAB plus 2EI by L into 2 into near end. Near end is what? Near end is A. So 2 into theta A plus far end is B. Similarly, vice versa is theta B, MBA. So these two equations are called actually slope deflection equations. So using these two equations, we can solve or we can compute the indeterminate structures. So now let's see an example how we can use this method or use these two equations to solve an indeterminate structure. Now let's see the question. A continuous beam carrying a uniformly distributed load of 2 kilonewton per meter in addition to a concentrated load of 20 kilonewton as shown in figure. So this is a beam, continuous beam, because if the spans are more than one, right? This end A end is fixed, C end is also fixed, whereas middle you have a roller support B. So it is a continuous beam. It has two loads are acting. One is this UDL is acting 2 kilonewton, and then 120 K and 20 kilonewton force is also acting here, concentrated force. So the question is you have to draw the bending moment and shear force diagram assuming that EI to be the constant. EI is constant, you have to draw the bending moment and shear force diagram for this beam. Now how to do that? So our first step is to restrain all the members. So this here two members are there, right? A to B, B to C, two members are there. So our step one is to restrain or to restrain all the supports. So A to B now, so A is anyway fixed given, B is not fixed, B is a roller support. But as per our step one, we have to lock all the support. So we make it lock. That's why this is the AB part, whereas this portion also fixed, and this is BC part. BC part also, this point is fixed. Both the ends are fixed. So when you fix both the ends, what will happen? And the loads also we have to give, right? So here 20 kilonewton acting and UDL is acting 2 kilonewton, whereas here only 4 kilonewton load is acting UDL. So when both the ends are fixed, fixed end moment will be generated. Fixed end moment MABF. So this MABF, MBF, both the fixed end moments are generated. So how much will be the MABF fixed end moment because of concentrated load and because of UDL both. So as we have seen in the last class, that is in the moment distribution method, fixed end moment, how we can compute, that is for concentrated load, it is PAB square by 12, right? So P is how much? P is 20. So 20 into A is from this side. How much is the distance? So this 3 kilometer, 3 kilometer, both 3 meter, 3 meter, both. So A is 3, B also 3. So P into A B square by L square, right? L square is here, L is total 3 plus 3, 6, 6 square. So this is the fixed end moment because of concentrated load, and fixed end moment because of UDL is WL square by 12. So W is how much? W is uh, 2, right? 2 kilonewton UDL, 2 kilonewton per meter into L square. L is 3 plus 2, 3 plus 3, 6, 6 square by 12. So this is the total fixed end moment at end AB, which is nothing but 21 kilonewton meter. Similarly, MBA also it will be minus 21, same value, just it will be minus opposite sign, minus 21 kilonewton meter. Now MBC, MBC is how much? So MBC is means is this part. So this part only UDL is acting. So the equation will be the fixed moment equation will be WL square by 12. Very simple. So W L square by 12. So here W is how much? W is 4 and L is also 4. So 4 into 4 square by 12. So which will get now 55.33. Similarly, opposite side it will be minus 5.33. So now fixed moment computation is over. So now simply substitute the values in the slope deflection equation. So here, as I mentioned, here we have to first find it out what how much is the kinematic degrees of freedom for each support. So here if you see support A is a fixed, means A cannot move in any direction. It is a fixed support. That's why theta A is also 0, right, in this point. So theta A slope will be equal to 0 because it is a fixed end, right? Similarly at theta C also fixed end. So this is also should be theta C also equal to 0. Whereas theta B is not 0 because it is a roller support, and that's what we have to compute. So theta B is our main objective to compute, to find out the value of theta B. This is unknown. Whereas theta A we know it is 0 because this end is fixed end, whereas theta C also 0 because this end is fixed end. Whereas theta B is not 0. So that we have to find it out. Theta B using the slope deflection equation. So let's write our slope deflection equation. Last slide we have derived this equation. MAB equal to a friction moment of AB plus 2EI by L into 2 theta A plus theta B, 2 times near end plus far end. So now theta A value is 0. Already I know, we know, right? Theta A is 0. So simply substitute theta A is 0. Now what you will get? MAB equal to friction moment of AB, which is nothing but 21. So 21 plus 2EI by L into L is how much? 6, right? Total is 3 plus 3, 6. Into 2 into theta A is 0. So this part, entire part will vanish. So only remains theta B. So MAB is over. Similarly, MBA also can be written. Just substitute the values and put theta A is equal to 0 and theta C equal to 0. So MBA is also done. Similarly, MBC also same equation, so just substituting the values, and C theta C also 0. Just remember this value and substitute all theta MBC, MCB. All four values are computed. Now next step is to use the compatibility equations. So what is this compatibility equation? So now if you see at B is a roller support. Roller support means uh, there is the reaction moment at this point is 0, right? Reaction moment at B should be equal to 0. Net moment about B should be equal to 0. So that is our criteria. So this is equation, we call it compatibility equation. Means all the moments about sum of all the moments at B should be equal to 0. So that's what we have kept here. So all the moments means BA and BC, right? So two moments, one is B to A this side, another is B to C this side. So moment BA plus BC both should be equal to 0. So now substitute BA value, whatever we computed, this is a BA equation, right? BA is this much, similarly BC is this much. So both the values you substitute here, and here only single unknown is theta B. So from here easily you can compute what is the value of theta B. So now theta B value is competition is over. Now we know theta A is 0, theta B value is this much 9.4 by A. Similarly theta C value is also 0 because this end is fixed end, right? So now this only one single kinematic degrees of freedom theta B that we have also computed what is the value, that is theta B is this much. Now easily we can compute all the end moments. So end moment MAB. So MAB A to B, right? This end. So this end MAB is not 0 because MAB is a fixed end, right? So moment should not be 0 at fixed end. Similarly at C also moment should not be 0. So what is MAB? So MAB already we computed, right? This is MAB. So now we know the value of theta B also. Just substitute the value of theta B in MAB. So you will get MAB value. What is the MAB? So this is MAB equation. So just substitute the value of theta B. You will get MAB equal to this much. So moment at end A is this much, 24.133. Similarly, MBA also. MBA is minus 14.733 and BC also it will be plus 14.733 because if you add MBA plus BC it should be equal to 0. So minus 14 plus 14. So net moment at B is 0. Similarly, MCB also this is the equation. So here you substitute the values of theta B, whatever you computed here. So you will get finally this is the MCB. So all the fixed end moments are now computed one by one. So that's how is actually we can compute all the fixed end moments using the slope deflection method. So now our main objective is what? Our question asks to draw the bending moment and shear force diagram. So we have to draw a bending moment and shear force diagram. That is our main objective. Although we have computed all the moments and slope also we know. Theta b also we computed. So now last part of this section is to draw the bending moment and shear force diagram. So how to draw bending moment and shear force diagram? First we have to find it out the reactions RA, RB, RC, all these reactions also we have to compute. Then only we can draw the shear force diagram, right? So how to find it out the RA and RB? So this is the first part, A to B portion and B to C portion, right? So two segments. So already we computed what is N moment. So 24.133 we just computed in the last slide. If you see MAB value is 24.133. Similarly M and BA is 14.733. This is also 14.733 and this is we computed 0.63. So this is just we put all the moments. Now find it out. So this is this free body diagram also in equilibrium, right? So just take all the moments about B should be equal to 0. Write down what are the equations you will get. So all the moments about B should be equal to 0. So find out what are the moments. RA into total distance 3 plus 3 6. So RA into 6, which is positive because it is a clockwise direction acting. Then you have what else? Another moment is acting at B, which is called positive 14.733. Then you have moment because of this concentrated load also, which is nothing but 20 into distance. 20 into distance is 20 into 3. So that's what minus 20 into 3 because the direction here is anti-clockwise. Minus, that's why. Now you have again another anti-clockwise moment that is 24.33. So minus 24.33. And you have UDL is also acting. So UDL is WL into L by 2. WL into L by 2. So this is you put. And from here you find out what is RA. RA means reaction, vertical reaction at A, which is nothing but 17.567. Now similarly RBL left side reaction, RB is left side. Similarly RB right side, from this diagram you will get RB right side and RC. So all these values, reaction values you compute easily, we can compute it. Now you can plot the shear force diagram. How we plot it? So if you see at A, how much is the reaction? RA we computed 17.576, right? So that's why here from here it is 17.576. Then UDL is because UDL is acting downward, so that's why it is downward moment. Now at from here again it will go down again because 20 is acting here, right? From here this drop will be 20, and then again UDL is acting, so it will go down. And from at this point, how much it is? At this point RBL is how much? RBL is 14.33, right? Upward. So 14.33 will act here. Now right side of RBL is 11.526, right? So from here it will be 11.526, again it will go up. Then again UDL is acting, right? B to C segment. So that's why this will be down. At this point RC, and RC is 4.47. So 4.47 again up. So this is the shear force diagram of this problem. Very simple. Now bending moment diagram. Already we computed what is MA. So MA is for 24.133, right? So 24.133 negative. Then you have UDL is acting, everything is acting, so this will be up. Again at this point, already you have something 14.733. So that's why at B it is 14.733. Again it will go up, and at C it is how much? 0.63. 0.63. So this is the bending moment diagram of this beam. So like that we can solve using the slope deflection equation very easily. You can solve the indeterminate structure and easily we can draw the shear force and bending moment diagram at any element. So we have to use the slope deflection equation, and then we have to use the compatibility equation to find out the unknown kinematic degrees of freedom, and then you substitute the equilibrium equations, find out all the reaction forces, and then you draw the shear force and bending moment diagram. So that's we are completing our this method, that is slope deflection method, with simple loading condition. So this is a deflection based method as we discussed earlier also, and this method can easily be written in a program, like we can easily write computer code to automate entire process. So thank you so much.